Cool. Okay, so um, yeah, my name is Bradley. I'm a master's student currently in the archaeology program at the University of Otago, and I'm going to be talking through some of the research that I did last year. So before we begin, I'd just like to quickly acknowledge Kati Huirapa ki Runaka Pukataraki, who are the kaitiaki or guardians of the site, which was used in this study. So in this, we're focusing on Maori fishing devices, but there's a bit of a gap there in that Polynesian settlers arrived in the New Zealand islands somewhere between 1250 and 1300, and we then don't have any more people arriving until Europeans in 1769. So there's at least 400, maybe more years in between. Now, at the time of European arrival, we have a couple of main line fishing types in use. We have pa which are thin, curved pieces of wood, and we also have these ones here on the left and middle of this slide, which are called poho manga or barracuda lures. And these are, again, just chunks of wood with a point put through, often a mammal tooth. But when we actually go through the archaeology, there's a bit of a discrepancy in that in our earlier layers of earlier sites, we actually have lures more like those on the right-hand side of the screen here. These are fairly large, triangular cross sections. They've got more detail and they're usually, if not exclusively, made of stone. Most of the work that's been done beforehand is largely classificatory, and the last piece of published work focusing on the lures in southern New Zealand actually came out in the 60s. So there's quite a gap to bring new methods in. With that, we decided to try and develop a method to investigate the use and behavior of these fishing devices, and then use that to try and determine whether the lure shank design actually impacts the way the lure behaves in the water. To this, we identified a site sample from Waihemo, Shag River Mouth. This is a fairly early, reasonably major site in the Otago region. It dates to the 14th century, and fishing is a major activity at this site. It's been extensively excavated. So from here, we tested two main lure shapes, a flat cross section and a triangular cross section. The first thing when we're looking at these is how are we going to test them? And the first thought that you might have is why not go fishing with them? Well, the fishing around New Zealand is quite seasonal. A lot of it is targeted when kahawai are schooling, and we just can't actually predict accurately enough to test when the fish are going to be there. The other thing is we would need a boat, which is really expensive because there would be animal involvement. We would need an ethics approval, and we're running on a very short timescale, so we likely wouldn't have actually had time to go through that process. And most importantly, we can't actually see the lure while we're doing this, so we actually have no idea why we're catching fish with some lures and not others. So that one's get ruled out. Then we thought, okay, what about trying to use computational fluid dynamics? We can make 3D models of the lures, which is a huge plus for our time constraints. but we needed to learn how to use the software, which we didn't have much time for. The options we had were time limited, and we were likely to need more than we could get with the free runtime, which means we would have to pay, and that software can be quite expensive. And again, we've got basically no budget. And while CFD would be useful for identifying the actual flow patterns created by the lures, we wouldn't actually be able to see how that relates to them in the water. So we ultimately decided not to do this as well and moved on to our third method, which was experimental, putting the lures in a flume and filming them in controlled water conditions. We can control the speed, we have a controlled flow, and we can easily switch between lures. Especially useful for this is the School of Physical Education here at Otago actually have a flume which they very kindly allowed us to use and did not charge us for. So this is the method that we went with. Our first step is we need lures to use. Obviously, we can't put the actual tauka in the water because they're very, very important to the tangata whenua, and they're also liable to be quite extensively damaged by that. What we did instead, we took them to the Department of Computer Science with the help of the Aotearoa New Zealand, who hold the items on behalf of the iwi, and these were scanned using an iron-scan 3D scanner. This created a 3D mesh model for us, and then we could take that mesh model, put it into Blender, and cut it to get cross sections, which we could use to make a sketch plan. Then we could use the sketch plan to guide us as we made replica lures by hand. We made the shanks out of argillite, nephrite, and serpentinite. These are the types of stone that come up quite frequently in the archaeological literature, and they're also, fortunately, quite easily available to us. Then we would add points made of beef bone and shanks, were lashed to the shanks using hemp cordage. So our process on the left here, we would start with a roughed out piece of rock. We would sketch our rough dimensions on it and cut it into a preform shape like what we have on the right. From there, we would sketch on the details, add this with hand files and a Dremel, and then eventually we would get to the stage on the right where we have a polished lure ready to lash a hook on. And once we get to that stage, we're ready to actually start testing it. So our experiment itself, this is the flume that we were able to use. It's quite a large area and it has a controlled laminar flow. So we always know that we're getting a nice consistent current. We have the window at the top. Behind that window is a camera, which we are filming this angle from. We would drop the lure in and let it settle on the bottom before turning the flume on. Then we would gradually run the speed up until we get to this stage here, where the lure is moving at a nice repeated pattern of movement. And we'd run this bit recording for a while so that we could actually get some good footage of how the lure is moving. From there, we would continue to run the flume up until the lure goes through the surface, and then we would gradually bring the speed back down again until it settles. And the reason for that is we want to make sure that we're not actually getting bad speed data, because in reality, when you're out in the ocean fishing, you're not going to sit still and wait for the lure to hit the bottom of the ocean before you start paddling. You're going to be paddling when you throw it out. After we've done this, we can move on to analysis. So in the flume, we had our side-on and top-down cameras, which were recording in high definition. At the start of each of those recordings, we placed a ranging pole in, and the reason we did that is so we can calibrate footage. To do this, we used a software called Kinovea. So Kinovea is a sports motion analysis software, and it can automatically calculate movement. When we insert the ranging pole, we can calibrate the measurement system in Kinovea, and then we can use this lovely little orange line that you can see in the image to project from point to point, measuring the displacement between the base of the flume and where the lure is actually floating in the water. Another really important tool that Kinovea has is the ability to automatically calculate angles. So to measure these angles, I would go through frame by frame, and I would place a marker at the start of the movement, and then another marker at the end of the movement. Then I could measure the angle between those two lure locations to figure out the maximum angular displacement. And I could repeat this for the other side, doing it for both the side-on and the top-down angles. All of this data, the angles and distances measured in Kinovea, as well as the speeds measured at the flume, were collected into Excel for graphing and were all p-tested. The results of those p-tests were that there was only one group of lures that were not a statistically significant result. We could then combine this with observational data to try and figure out how the lures would have actually been used. Our key results from this, when we go through the digital analysis, the longer the lure is, the greater the angle it will move to. So we're talking quite substantial, smaller lures moving about 15 degrees, whereas the larger lures are going to nearly, and in some cases over 30 degrees of lateral angular deviation. So it's quite a substantial change. We also saw that the shape of some of the lures appears to generate lift, and I'll talk about this a bit more on the next slide. Our flat cross-sectioned and triangular lures moved differently. So in this diagram on the right of the screen here, when our triangular lures were exposed to a current, they mostly rotated around the Z-axis, almost like a tail wagging motion, whereas the flat cross-section lures actually rotated around the X-axis, almost like they were wobbling from side to side. And we could also see that the lures were very sensitive to asymmetry. On some of the lures, being shiny, highly polished rock, the lashing knots were able to slip from one side to the other, and when this happened, the lure would pretty much flip entirely onto its side. Our implications were that the longest lures would be detectable from furthest away. So fish don't just hunt by eyesight, they actually have sensors in their face that allow them to detect disruption in the water. So a larger lure is going to create more disruption and be more likely to attract the attention of a fish. Our lures were able to be used at much lower speeds than we had assumed, even for the large examples. There's a bit of an assumption that we make from, I suppose, a Eurocentric position that when we're looking at these large lures, and there are some out there that are a foot even larger in size, that's too big to catch anything with. But we actually found that if these were symmetrical, they could be stable. The largest lures we tested in this study were about 16 centimeters long, and they came through breaching the surface, which is faster than you would need to go to use them, at about 2.8 meters a second. Just for a bit of context, fastest record for Michael Phelps swimming was 3.9 meters per second, and the average trained swimmer, say in your local swim club, usually swims at about 2.4 meters per second. So that's really actually quite a leisurely pace. Because these large lures would have been able to easily be used, we can suggest that size alone is not a reliable indicator of usability, and that we perhaps need to take a closer look at how the lure actually functions and what these large lures could have been able to catch, as opposed to just presuming they're ceremonial or social objects. The sensitivity to symmetry suggests that the lures are quite finely balanced, so there's a high degree of craftsmanship needed to make these lures in a way that would have had reproducible behavior. And most importantly, our method works, and we can use this software to test the in-water behavior of the lures. So where are we going to next? Currently, we're using this study and expanding on it as a basis for my Master of Arts thesis to investigate the role of the lure in targeting for specific fish species, and then relating this fish targeting back to human environmental interactions in the marine environment. Also, there's a strong similarity in these early Māori lure forms to those in the wider Pacific. Samoa, Tonga, and the Society Islands, as far as I've seen, all have very similar lures available in them. And perhaps we can look at links there. And I'm hoping to be able to use it in conjunction with other techniques like the CFD that I discussed earlier to help explain the results of the study. For example, a lure is moving a certain way. We've observed that. Now let's put a model of that lure into CFD to try and identify which areas are causing that motion. I do have to thank also the Aotearoa New Zealand for their help. Ngāi Tahu, again, as the Kaitiaki Coastal People Southern Skies Centre of Research Excellence, and Polynesian Society for providing the research funding, and Zach, Karen, Gerard, and Lana for their help supervising me and running around getting all of my lures out of storage for me. So thank you all for listening. Let me know if you have any questions.